Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello and welcome to another module of the Design Patterns training. My name is Martin Schroeder at swedishembedded.com. If you have any questions regarding this training, you can always join our Discord channel. You'll find the link at the top right corner of swedishembedded.com, or you can email me directly at martin.schroeder@swedishembedded.com. In this module, we're going to look at the Mutex pattern, and this is the primary pattern that we use for mutual exclusion between threads. So we talked about the spin lock pattern, where we can get mutual exclusion between CPU cores and between interrupts and other code. We looked at the semaphore pattern, which we use for signaling. But when we want to do mutual exclusion between threads, there is a few more things that we need to take care of. And so we need to have a separate pattern for doing that, and we call this the Mutex pattern. The defining characteristics of the mutex is we have two basic operations. We have the lock operation and the unlock operation. The mutex is primarily designed for mutual exclusion between threads. So unlocking a mutex, for example, is invalid from a different thread than the one that locked it. And there's a few other rules that we need to follow. The mutex locking operation does not disable interrupts for the duration of mutex being locked. So we don't have the same effect as, for example, with a spin lock, where we would be missing events if we don't unlock on time. And the mutex itself actually also maintains a thread queue. So it's a fully thread-aware primitive, just like the semaphore. But the mutex does a little bit more in terms of controlling the priorities of the threads. So, for example, a mutex can increase the priority of a thread if another higher priority thread requires the mutex. And there's a few more implementation details which we're going to look at in this module. And with mutexes, recursive locking is also allowed as long as it is the same thread that is locking the mutex. So by definition, you can see that there is no way you can use a mutex from an interrupt, for example. It just doesn't make any sense. The mutex is primarily designed for thread synchronization. We use mutexes to guard against mutually exclusive access to variables. So whenever we have some data structure that needs to be shared between multiple threads, we use the mutex to guard for access to that data structure between those threads. And the mutex is the primary way in which we ensure thread safety of our code. So whenever we want to have some part of our code to be thread safe, the mutex is the first primitive that we look at to ensure thread safety, to ensure safe concurrent access to the shared data structures. The benefits of this pattern, and compared to, for example, a semaphore, which technically you can also use a semaphore for mutual exclusion, but it just doesn't really provide us with all the necessary functionality. So the benefits of the mutex pattern is that we have built-in priority inversion avoidance by means of increasing the priority of the current thread that is holding the mutex if another higher priority thread needs the mutex. And the mutex is also very easy to use. So it's very similar to how a spin lock works, or it's very similar in usage to the spin lock, but the mechanics of it are geared towards thread safety and not any other purpose, as with a spin lock, for example. The drawbacks of the mutex pattern is that it's typically locked to a single resource that we want to guard. So we would have different mutexes for different instances of objects that we share between threads. And the other drawback is, of course, that it only supports threads. It doesn't support any other way of any other type of concurrency that is present in our system. But we can live with that because we have the other primitives specifically designed for handling other types of concurrency. All right, let's move into the implementation of the Mutex locking and unlocking functions. I'm going to walk you through in detail exactly how we implement Mutex locking and unlocking. We're going to use a spin lock as a way of guaranteeing that our access to all of the internal data structures of the Mutex is concurrency safe. And we're going to look at how we actually increase the priority when we do it and how the whole logic works. But first of all, I want to explain a few key mechanics of the Mutex itself and how it's designed to work. So if the Mutex is locked, then if we try to lock the Mutex again by the same thread, then we just return a success because it is perfectly legal to try to lock the same Mutex by the same thread. So we can have nested functions that for example, if we lock the mutex and then we call another function that also tries to lock the mutex, that operation is perfectly valid because our current thread is still the owner of that mutex. So that operation is very cheap. It just returns success and then basically increases internal counter so that we keep track of how many times we have recursively locked the mutex. But the reality is that we can just successfully return. If the mutex is already locked by another thread, then and we try to acquire it, then our current thread needs to be placed on the wait queue of the mutex so that we can then retrieve our current thread from this wait queue when the mutex is unlocked by another thread and switch to our current thread instead. If the mutex is already held but is held by a lower priority thread, then we need to increase the priority of that thread so that it executes faster, so that our thread, which has the higher priority, can acquire the mutex quicker. And if there are threads in the wait queue during the unlock operation, then we need to switch to the first highest priority thread in the wait queue when we unlock the mutex so that it can continue. Let's look at the lock-in operation first. So first of all, we have a static lock here, a spin lock, which we use for guarding access to the internal data structure of all mutexes together. There is really no point in making this spin lock per instance variable. That would just be wasting memory. So we create a static variable here that is shared among all mutex instances in our application. We then check if we are inside an interrupt. So locking a mutex in an interrupt is an invalid operation. The mutex is not aware of interrupts. So if we run into the situation where we try to lock the mutex from interrupt code, we need to generate an assertion. Next, we acquire the spin lock. After this point, once we execute this function, we have exclusive access to all mutex internal data structure. So we check if the lock count is 0, which means the mutex is unlocked, or if we are the current owner of the mutex. So in any case, we store the current owner priority, we increase the lock count, we set the current owner to the current thread. So this is in case we have this condition true, but not this condition. So we still just assign the owner. And the mutex stores the owner of the current owner of the mutex. So that would be the current thread. And then we simply unlock the spin lock and we return success. So locking a mutex, if the mutex is unlocked and we try to lock it, it's a very cheap operation. It doesn't involve any kind of context switch. The only place where we run into a context switch is if the mutex is currently locked by another thread and we try to lock it. So then we go to handling of the timeout and the pending of the current thread. So if the timeout is set to no wait, then we simply unlock the spin lock and we return eBusy. So this means basically that the mutex is currently locked. So this condition was not true, which means that the mutex is currently held by another thread. So we check if there is a timeout supplied by the user. If there is no timeout, then we just return eBusy. So that's the requirement of no wait timeout. If the timeout is non-zero, then the next thing we do is we get a priority of the owner thread, and we make sure that we check this priority, and if if our current thread priority is higher than the priority of the thread that owns the mutex, then we need to adjust this priority so that the mutex can be released faster. And then we call zpend car, and this basically pends our current thread onto the mutex wait queue with a timeout. And we supply also our spin lock and the spin lock key variable that corresponds to the state of the interrupts that we need to restore the interrupts to. And once our thread is properly pended, then this pending operation unlocks the spin lock. And if this operation was successful, then that means that we have acquired the mutex, and so we just return 0. Now, if the pending operation returns non-zero status, that means that there was a timeout, and so we need to now handle the timeout. So we get the spin lock again. We get the first thread that is waiting for the mutex off of the wait queue. We adjust the priority, and we then, if we need to reschedule, we call reschedule, we switch to that thread, or otherwise we unlock the spin lock and we return that we need to try again. So basically there was a timeout, so we need to try again. So that was it for the locking operation of the mutex. Now we look at the unlock operation. So when it comes to unlocking the mutex, we need to make sure that we're not in an interrupt, because using mutex in an interrupt is completely invalid. We need to check that the mutex is currently owned by some thread. It's not valid to try to unlock a mutex that hasn't been that hasn't been locked, basically. And the next thing we need to do is check whether the owner of the mutex is the same as our current thread, because if we are not the owner of the mutex, we cannot unlock that mutex. So if we are not the owner, we return permission error. Now, the next thing we check is whether the lock count has been increased, which means that the mutex is actually locked. And attempting to unlock a mutex which is unlocked is obviously invalid. So we need to assert for this and catch this case as well. If the lock count is more than 1, which means that we have recursive locking, then we simply unlock and return. So we simply return success here. So if there is a recursive locking of the mutex, then we just keep the mutex locked basically, and we return success. Next, we acquire the spin lock, and we do so now that we have gotten here, this means that the mutex is locked, and we are the only owner of the mutex, or we are the owner of the mutex, and this is the last place before we actually truly unlock the mutex. So there is the lock count is 1, and so it means that now we are actually unlocking the mutex. So it's time to switch to whatever thread is waiting for the mutex, if there are any threads waiting for the mutex. So what we do is we unpend the first thread. So the new owner becomes the first highest priority thread on the wait queue, waiting for the mutex to be unlocked. And we set the mutex owner to the new owner, and we then call, we ready that thread, we mark it as ready, and then we call reschedule with the spin lock, so that the spin lock is unlocked when the reschedule has completed, basically. And if there are no threads waiting for the mutex, then we simply set the lock count to 0, we unlock the spin lock, and we then return successful. So now we have unlocked the mutex. So as you can see, if we have a mutex that is not being locked by another thread, then locking and unlocking operation is very lightweight. There is basically just a brief locking of the spin lock when accessing the data of the mutex, and then we just return success in both cases, in both the lock operation and the unlock operation. So go back through this code listing and really try to understand what's going on here. The concept is really simple, but there is a lot of little intricacies in how this is implemented. And when you understand how this mechanic works, it becomes very intuitive to use mutexes in your application, and you know what to expect. You know that if you try to avoid concurrent access, in general in your application, if you don't share too much data between threads, then having mutexes in place is a very lightweight operation. You would never be pending on a mutex basically, and in that case, it's a very lightweight operation. It doesn't really cost much to have it in place. So that's it. Let's move to the next slide. The best practices of using a mutex is that, number one, you should be using object-oriented design from the start. So you need to apply the object pattern, which I described in the first module of this training, because that gives you a clear indication of what data is actually being shared. So you can have a mutex inside your object, and that provides a very clear indication that that mutex is the mutex that is being used to guard access to all the data that is part of this self pointer that you're using. So if you have global data, it becomes a little bit more ambiguous of what data you're actually locking using a mutex. But if you have an object-oriented design, it becomes very simple and very easy to maintain. Number two is use the concept of locking data and not code. So don't hold a mutex over multiple function calls and other operations. Try to minimize the amount of locking that you do so that you can avoid this expensive or potentially expensive queuing of your thread and then dequeuing of your thread when the mutex becomes available. If you lock data and not code, you minimize the possibility that the mutex is going to be locked when you try to acquire it. And if you use mutex, for example, in places where you have multiple work queue items executing, so let's say you push a work queue item on the system work queue, and the operation that executes in response, like when you run that work queue item, let's say that operation requires you to acquire a mutex. If you have to delay when trying to wait for that mutex, that's gonna pause all the other work queue items that are currently waiting in the same work queue. So a better approach there, and actually the recommended approach, is to reschedule the work queue item instead, and to try to acquire the mutex with no delay parameters, so you don't get queued on that mutex. And then if you cannot acquire the mutex, you just reschedule the work queue item so that it runs again at a slightly later point in time, and then you try to acquire the mutex again. And by doing so, you let other work queue items run before you try to acquire the mutex again. Common pitfalls when using a mutex. Number one is deadlocks. So if you have multiple mutexes and you lock them in different order, then you can run into a situation where you have two threads waiting for each other. So when you lock and unlock multiple mutexes, you should always lock them and unlock them in the same order, or basically unlock them in the reverse order, but it's still, those two orders have to correspond. So if you have mutex A and mutex B, and you want to lock them both and unlock them both, then you need to lock mutex A, then B, and then unlock mutex B and then unlock mutex A, and not unlock mutex A and then unlock mutex B, because then you can have two threads trying to acquire those mutexes, and they would be locked together and you'll have a deadlock. And number two is thread starvation. So if you have a high priority thread that takes the mutex, holds it for too long, and then releases it, and then maybe acquires it again. Let's say the thread is running in a loop, and it's basically acquiring the mutex and doing something and then repeating the loop. Then you can have starvation with regards to other threads. The other threads will never be able to acquire the mutex because it's always your thread that is holding the mutex. So they will never be able to continue. So that's something to watch out for as well. And this last point is best solved, of course, by locking data and not code. So just lock the data access, synchronize access to your shared variables, and then when you need to do operations on data, you just copy the data out, you do the operations, and then you lock the data again. But of course, you have to be attentive not to get into situations where you actually need to have exclusive access for the whole duration of whatever you're trying to do with the data. So concurrent programming is tricky. It's not. It does require you to think about more details of implementation. Think about what can happen outside of the code you're currently writing. So concurrent programming always comes with those little quirks and details that you need to pay attention to. The main alternatives to mutexes is what we discussed before, the semaphores. They're very simple, but the use case is slightly different. And conditional variables, we're going to look at that in the next section, where we'll look at how we can use a mutex together with a conditional variable, and where we can wait for specific conditions to occur, specific dynamic conditions. So conditional variable is a slightly more complex pattern that builds on the mutex pattern and adds extra functionality to it. Let's check your understanding of this pattern. So why is it illegal to lock and unlock a mutex from an interrupt handler? What key functionality does this design choice make possible? So if you were to allow mutexes to be locked and unlocked in interrupt handlers, what implications would that have? Why is it the case that mutex cannot be locked by one thread and then unlocked by another thread? Why do we want to make sure that we don't unlock the mutex by a different thread? What happens to a lower priority thread if it is holding the mutex and is currently suspended when a higher priority thread tries to acquire the same mutex? What changes do we do to its priority level? And why do we do that? If multiple mutexes are locked and unlocked, in what sequence should those mutexes be locked and unlocked to avoid a deadlock? So if you have mutex A and mutex B, how should you be locking these two mutexes, and how should you be unlocking them? So that's it for this module. I hope you learned something, and I'll see you in the next module.